Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Seismic Structure, and it is going to provide you how to reduce vibrations using base isolation and damper systems. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the earthquakes, and then focus on the base isolation and damper systems before wrapping up with conclusions. Okay, earthquakes have always been a terrifying phenomenon, and they have become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. If you have watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart. But that is not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So, what is actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single line top with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes are not actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and the lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. During the quake of 1985 Mexico City earthquake, many buildings between 6 and 15 stories tall collapsed. What is strange is that while shorter buildings keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized buildings that collapsed were observed shaking more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency, an oscillating system. The frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So, in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. Engineers have devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. For the base isolation system, a simple structure with a base isolation was designed to illustrate the benefit of adding base isolation. The method of multiple degrees of freedom was used. Displacement of each story denotes independent generalized degrees of freedom with the corresponding external forces. In order to analyze the structural models, we can use Lagrange equations. In the calculus of vibrations, the Lagrange equation is a second-order partial differential equation whose solutions are the functions for which a given functional is stationary. Let T and V denote the total kinetic and potential energies. Then the equations of motion are given by the two equations. For sake of simplicity, consider an unforced system. In this system, either phi is 0, which means the structure doesn't move, or the matrix in parentheses must be singular and have a 0 determinant. The mass of the base isolation is m1 equal to 1 and the stiffness k1 equal to 2. The mass of the building structure is m2 equal to 2 and the stiffness k2 equal to 4. So the structure can oscillate either with omega 1 equal to 2.7321 and omega 2 equal to 0.7321. Omega 1 and omega 2 are natural frequencies. If we substitute omega, we can find phi. Phi 1 and phi 2 are called eigenvectors and mode shapes and can be scaled arbitrarily. Considering scaling mode, the maximum displacement of the first and second mode is 0.6845. It is less than 1, so it means that the base isolation is useful to reduce vibrations. Next system is the tune mass damper, and we can call it as TMD. A TMD reduces the amplitude of vibration by absorbing kinetic energy from the system. A typical example is the Taipei 101 Tower. Rather than hide the spherical tune mass damper, the building's designers chose to open it to the public. Taipei 101's TMD has become a draw for tourists and even has its own mascot, the Damper Baby. The publicity associated with the Taipei 101 has sort of unveiled this really cool bit of engineering. That is the tune mass damper. So how does it work? We can construct this model of a pendulum-based tune mass damper in a skyscraper to see the difference between a structure without damper and with damper. If we lock the pendulum and set the building swaying, we can get a sense of how it would perform with only the building's own natural damping. Plotting the acceleration response, we can see that the model experienced the maximum amplitude. We can also see that the building has some natural damping just due to the internal friction in its movement. Otherwise, it would just sway indefinitely. Let's try the exact same experiment with the pendulum able to swing freely. Looking at the plot of acceleration response, we can see that the amplitude was smaller than the structure without damping. Therefore, in order to analyze the tune mass damper system, we can focus on the amplitude. Here we simplify a tall building as a primary mass m1 and the tune mass damper as mass m2, assuming that the damping force is proportional to velocity and there is a periodic force PO times sine omega t on m1. It is easy to work out the differential equations governing the motion of the system. We also simplify slightly by letting C1 equal to 0 and get the following equations. Our goal is to grind through calculations and find explicit expressions for the periodic solutions to these equations. We find a periodic solution in the form as U1 and U2. Substitute the expressions into basic equations and solve these equations to find the amplitude of the main mass. After the derivation, we can obtain a new expression for the amplitude of the response of the primary structure. If assume natural frequency ratio f equal to 1 and mass ratio mu equal to 0.05, the relationship of forcing frequency ratio versus amplitude ratio shows in this slide. The damping ratio increasing brings larger response of the system. However, if the damping ratio is very small, the response of the system has two peaks. We need to control the damping ratio to determine the optimum tune mass damper. From conclusions, what we learned: natural frequency is the most dangerous situation in earthquakes. For solving the problem of oscillation in buildings, both of the base isolation system and the tune mass damper system are useful to reduce vibrations. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.